in the previous lecture, we have started to deal with the applications of Fermi Dirac statistics, or you can say the applications of Fermi Dirac distribution law. And in this regard, in the first lecture, we have discussed in very detail the concept of density of states. Okay, and you have also learnt that how we can find the number of electrons or free electrons in a metal in a given energy range. Now today our aim is to discuss Fermi and the concept of Fermi energy or Fermi level, which is a most important concept to deal with the physics of metals, or you can say the free electron theory of metals proposed by Sommerfeld. So this will be a very helpful, very useful and very interesting lecture. Okay. As we will need the results of the previous lecture in discussing the concept of Fermi energy. So for your convenience, I have mentioned here the two important results which we have already obtained in the previous lecture. You have seen that the density of states, which means the number of quantum states in energy range between E and E plus d, which is actually denoted by the symbol G of E dE. You have seen in the previous lecture that this G of E dE is equal to 4 pi V over h cube times 2m to the power 3 by 2 times e to the power half dE. Okay. Actually here this V represents the volume of the potential box, which we have assumed cubical. M is mass of electron, h is Planck's constant, and E is energy of the electron. Okay. Now we have assumed that this 4 pi V h cube divided by 2m to the power 3 by 2 by the constant C. So in brief, we write G of E dE equal to C e to the power half dE. Okay. For convenience or to remember this result, we write this equation in this form. Now you have also seen that the number of electrons occupying the states between energy E and E plus dE is given by N of E dE equal to G of E dE times F of E. You can remember this F of E is what? This is actually the occupation probability. Okay. Or you can say that this is Fermi Dirac distribution function. Okay. Fermi Dirac distribution function. These two results have been discussed in the previous lecture. Now utilizing these results, we can easily understand the concept of Fermi energy or Fermi energy level, which plays a very vital role in discussing the Sommerfeld theory of free electron theory of metals. Okay. So now let us consider that the total number of electrons in this metallic specimen is equal to n. Okay. And you know that this N of E dE, this represents the number of electrons having energy between E and E plus d. So it is obvious that when we will integrate this N of E dE for the entire range of energy of electron, then you will get the total number of electron. So what will be this N? This N can be written as integral of N of E dE from 0 to infinity. Mark here, actually E is the energy of free electron, which means kinetic energy of free electron, and the upper limit is infinity. It means we are assuming that the highest energy of electron may be infinity. It is a classical concept. In classical physics, the energy of electron or any particle may be infinity. As I have told you earlier, that Sommerfeld's theory is a semi-classical theory, because in the development of this theory, so many aspects of classical physics has been adopted. At the same time, considering the Pauli exclusion principle and the spin of the electron under account on the distribution of electron, quantum mechanical aspect is also considered. So this is called semi-classical theory. So infinity is the upper limit of energy of electron, which is a classical concept. Okay, but you have seen that this n of E dE is equal to this much. This is g of E dE times f of E. Okay, so n can be written as I have written in this equation number 1. Okay, now you know you have studied in the first lecture that this Fermi Dirac distribution function f of E, which is also called occupation probability. Actually, this is the probability of electron occupying an energy state of E. It means when the electron is found in an energy state of E, what is the probability of finding of the electron in that particular energy state? That is measured by this probability function f of E. And you know, this f of E is equal to what? This is 1 over 1 plus e to the power E minus EF divided by kT. And this EF in this equation is called Fermi energy or Fermi energy level. And the K is Boltzmann constant, T is temperature. Now you can see that the value of this occupation probability actually depends on two factors. First factor is E, that is what is the energy of the electron. That will determine f of E. And the another important factor affecting the value of f of E is T. Okay. So at different temperature for different value of energy E, the occupation probability will be different. Okay. Here we are considering a particular temperature, and that temperature is 0 Kelvin temperature. This is also called absolute zero. So if you consider that our metallic specimen is at absolute zero temperature and we are considering energy of electron which is less than this EF. So if you want to find the probability of finding of an electron in an energy state which is less than Fermi energy at 0 Kelvin temperature, what will be that probability? You can see this occupation probability at 0 Kelvin temperature for energy less than EF will be equal to what? This will be 1 over 1 plus. Now see, since E is less than EF, so E minus EF, this will be something negative. Something negative. And when you will divide it by kT, but T is 0, so you will divide it by 0, and so this will be something negative and divided by 0. You know that when something negative divided by 0 will be what? This will be minus infinity. Okay, this is minus infinity. So in this condition, the power on this exponential is minus infinity. But you know, e to the power minus infinity is 0. So f of E will be equal to 1 over 1 plus 0, that is 1. It means at 0 Kelvin temperature, energy of an electron will be less than EF. What is the probability of this event? The answer is 1. Probability is 1. When you say probability is 1, it means the probability of finding of electron in an energy level below the Fermi level is 100%. Is 100%. In other words, you can say that at 0 Kelvin temperature, all the energy levels below the Fermi energy level will be completely occupied by the electron. they are actually completely occupied energy states. Electrons are there. Okay. Actually, I have shown this in this figure. You can see this deep line represents the Fermi energy level. Okay, at 0 Kelvin temperature in case of a metal. Okay, and these horizontal lines represent the different energy levels. I have marked here, you can see that when temperature is 0 Kelvin, then all these energy levels are occupied by the electron, those energy levels which are below this EF. So I have marked it that these are occupied states. Okay. Now let us see what will happen when temperature is 0 Kelvin, but we are talking about those electrons whose energy is greater than EF. What will be the probability of finding of an electron in an energy state whose value is greater than EF at 0 Kelvin temperature? Let us see. Since E is now greater than EF, so in this case E minus EF, this will be something positive. Okay, and when you will divide it by 0, when a positive number is divided by 0, the result is plus infinity. What will be the result? This is plus infinity. So here f of E will be equal to 1 over 1 plus e to the power plus infinity. But e to the power plus infinity, you know, this is equal to infinity, and so this will be 1 by 1 plus infinity, and this is 1 over infinity, and that is equal to 0. So this occupation probability in this condition is equal to 0. When you say that occupation probability is 0 for the electrons having energy E greater than EF at 0 Kelvin temperature, what does it mean? It means all the energy states, all the energy levels, or all the quantum states above the Fermi level are completely empty, completely unoccupied. No electrons are there in an energy level above the Fermi level at 0 Kelvin temperature in a metal. Okay. So particularly at 0 Kelvin temperature, you can see that this f of E has two discrete values. For E less than EF, the probability of finding electron in energy levels below EF is 100%. All the states below EF will be occupied, and all the states above EF are unoccupied. And if you want to find the total number of electrons which have been defined in this equation 1, then you can see that the limits of this integral, which runs from 0 to infinity, can be broken, can be divided in two parts, because this f of E has not same value in this entire energy range. Actually, between energy 0 to EF, you can see that f of E is equal to 1. This is just a step function. And between EF and infinity, the value of this distribution function is 0. So definitely, if you want to evaluate this integral, then it will be more convenient that we will divide this limit of integration in two parts, from 0 to EF and EF to infinity. Okay. So you can see I have written that this n is equal to integral of g of E dE Fe from 0 to EF. Okay. And plus integral of g of E dE Fe from EF to infinity. Okay. And as you have seen that in this energy range between EF and infinity, this f of E is equal to 0. So this second term will vanish. Okay. And hence you can write that the total number of electrons will be simply integral 0 to EF G of E dE, okay, and F of E, okay, F of E. And F of E, you know, in this energy range is equal to 1. Okay, you have seen this F of E is equal to 1. So this integral will be simply equal to integral 0 to infinity G of E dE. Okay. Now you have seen earlier that this G of E dE is equal to C e to the power half dE. Okay. So let us substitute the value of density distribution function G of E dE. So you can write N is equal to what? This is integral 0 to EF, okay, and C e to the power half dE. Actually, we will substitute the value of C later on after simplification, okay. And what will be this integral? C is a constant, and this e to the power half will be integrated, and when we will substitute the limit, you can see this will be equal to 2 by 3 EF to the power 3 by 2. This is the value of N. Okay, and say this is equation number what? This is equation number 2. This is equation 2. Okay, and now actually I have considered it as an equation because this will be used in the further calculation. Now from this result you can see that this EF to the power 3 by 2 equal to what? This will be 3n divided by 2c, okay, and so EF is equal to what? This will be 3n divided by 2c and whole to the power 2 by 3. 2 by 3. Now, you have seen that this constant C is equal to what? This is 4 pi V divided by H cube times 2m to the power 3 by 2. This is the value of C. And so when you will substitute this value of C here, then the expression for this Fermi energy EF will be equal to what? After substituting and simplifying, you will get that this expression will be h square over 2m times 3n divided by 8 pi v a whole to the power 2 by 3. After substituting the value of C, you will get this result. Okay, and this is also an important expression for the Fermi energy EF. But now you can see this N by V. N is the total number of electrons and V is the volume in which these electrons are found. So this N by V represents the number of electrons per unit volume. Or you can say this is the number density of free electron, and we denote this by this small n. This is number of free electrons per unit volume. Per unit volume. Okay, per unit volume. So in terms of this number density, you can write the expression for this Fermi energy. This is h square over 2m, h square over 2m times 3n divided by 8 pi. 8 pi and whole to the power 2 by 3. Actually, this is the expression for the Fermi energy EF. And you can see that this value of this Fermi energy is not a universal constant for all metals, but it will vary from metal to metal, because this n, which is equal to n by v, that is number of free electron per unit volume, this will be different for different metals, and that's why the Fermi energy will have also different value for different metals. Okay. Now, after getting this result, you can easily define what is this Fermi energy. You can see this condition that actually Fermi energy is the maximum energy possessed by electron in a metal at 0 Kelvin temperature. It means, or in other words, you can say that the highest and occupied energy level in a metal at 0 Kelvin temperature, that is called Fermi level. That is called Fermi level. And energy corresponding to that level is called Fermi energy. So you can say that the highest occupied energy level at 0 K is Fermi level. Fermi level. And energy corresponding to that is called Fermi energy EF. Actually, this Fermi energy or Fermi energy and Fermi energy level plays a very important role while we discuss the physics of metals and physics of semiconductor. Okay, we in the course on solid state physics we will study semiconductor, and then you will find the application of this concept of Fermi level there invariably almost in all cases. Okay, so thank you very much.